Hi everyone, so the focus of today's lesson is on types of radiation insults. The objectives are to differentiate between high and low linear energy transfer, to explain the relative biological effectiveness, summarize the effects of irradiation on somatic and genetic cells, and explain what direct action of radiation is and what an indirect action of radiation is. And looking at indirect, we will be discussing interactions of ionizing radiation with water, free radical production, and the reaction of the free radicals in relation to the body. So what is a radiation insult? It is basically an injury that is caused by radiation. So we will be differentiating between high and low linear energy transfer. Linear energy transfer is often just referred to as LET, and it's the amount of energy that an ionizing particle transfers to the material per unit distance. So it's the action of radiation inside the matter, what it does when it reaches there. The linear energy transfer depends on the nature of the radiation, of course, as well as the material it's passing through. The higher the concentration of the deposited energy, the more damage there'll be. And so linear energy transfer helps explain why radiation damage is sometimes disproportionate to the dose that's absorbed. High linear energy transfer types of radiation deposit a large amount of energy over a short distance, whereas low linear energy transfer deposits less energy per unit length of its track and travels over a longer distance, like X-ray and gamma ray. Linear energy transfer not only describes the rate at ionizing radiation is transferred to the soft tissue, but also defines the average energy deposited in the body tissue along the path of entry, and it is usually measured or represented in units of a kiloelectron volt. Now, low linear energy transfer radiation like X-ray and gamma ray, they mainly cause indirect damage to biological tissue, and this can usually be reversed and repaired. And then there's high linear energy transfer radiation that usually causes damage that cannot be undone. Now, the quality factor, or the Q factor you see here to the right of the slide, is a symbol for expressing the linear energy transfer response to the biological system or to the tissue. And as you can see, the protons has a quality factor of 5, and alpha particles have a quality factor of 10 to 20. And this represents the strength of that or those particles and its capability of causing damage. As you can see, X-rays, gamma rays, and even beta particles, they all have a Q factor which is equal to 1. So although they are harmful, they are not as harmful as alpha particles with a quality factor of 10 to 20. So what is relative biological effectiveness? The relative biological effectiveness, often abbreviated as RBE, is the ratio of the biological effectiveness of one type of ionizing radiation relative to another type, given the same amount of absorbed dose of energy for both of these types of radiations that we're comparing. So when assessing the RBE, X-ray is normally used as a standard or as a reference radiation, and that amount is 250 kilovolts of X-ray. If you wanted to determine the quantity of radiation dose of a certain type of radiation that is necessary to produce the same biological reaction or effect, this is how you do it, by using this formula and calculation. So in other words, RBE can be used to compare radiations with different linear energy transfers to determine its particular biological reaction or effect. So now you know from a prior lesson that absorbed dose is the energy absorbed per unit mass of the body tissue. But we also know that all types of radiation are not created equally. Equal doses of different types of radiation produce different biological effects, or relative biological effects, which is all to do with the pattern of energy deposition or transfer of that ionizing radiation energy. And we'll look at that more closely in a minute. So it is the relative effect on the body, and this will depend on how the energy is deposited or the linear energy transfer of that radiation. Does it follow a straight track and damage a lot in its path? Or is it dispersed? Or is it attenuated? Is it absorbed? Is it scattered? Does it transmit through the body easily with less damage? Or does it cause a lot of damage along the way? So that's what we will look at in a moment. But before we move on to the next point, I'd like you to try and attempt this calculation. Pretty simple. So here you can see in this formula right here, it takes about 40 millisievert of 250 kiloelectron volts of X-ray to produce cataracts. And it takes only 8 millisievert of alpha particles to produce cataracts. So we have to just determine, based on these two, we're comparing these two, what is the relative biological effect? And in this case, it is said to be 5. And what does this mean exactly? So what it means is that the average number of ion pairs that are produced per unit length of the body tissue it is penetrating through is 5 times greater for alpha than it is for X-ray. So basically the alpha is 5 times more deadly, let's put it that way. Now I want you to try and solve this problem on your own, which is at the bottom of the slide right here. If it takes 15 gray of 250 kilo electron volt X-rays to produce erythema, being skin reddening, and only 5 gray of alpha particles, what is the relative biological effectiveness? So now we're getting to the effects of the radiation that has been transferred to the body tissue per unit length of track. Now this image right here comes straight out of the textbook, the radiation protection textbook, and is on page 132, chapter 7. You guys can read up on this a little bit more if you wish. But biological damage for ionizing radiation can be seen on 3 levels: on the molecular, on the cellular, and on the organic level. And any visible radiation injuries always begins at the molecular level. Molecular damage results in the formation of structurally changed molecules that may impair its function. So the effects of radiation could be somatic and it could be genetic. Somatic refers to radiation dose to the entire person, and it is a sufficient number of cells are affected and damaged that the entire body process may be disrupted. Now, somatic effects are usually linked to long-term effects like cancer, and genetic effects are also linked to long-term effects. They are effects from radiation which occur to the offspring of the person who received the radiation. So think of Chernobyl, for example. Their kids and their kids' kids developed genetic effects as a result of that exposure. If the reproductive germ cells are damaged, then that damage may be passed on to future generations, and this is what occurred in the time of Chernobyl. Then let's look at deterministic and stochastic. So like I said, somatic effects are linked to long-term effects, and those effects are also referred to as stochastic. Stochastic refers to the probability of there being damage to particular cells or the body overall. Stochastic specifically relates to cancer and genetic effects. They can occur randomly. There's a probability that it may occur. So I used this example in Zoom the other day when Mohammed was asking the question, stochastic or long-term? Let's use smoking as an example. So say you're a smoker and you smoke a packet of cigarettes a day for the next 10 years. After 10 years of smoking that way, there is a probability, a chance that you may develop lung cancer. And it's the same with stochastic effects of radiation. After receiving little amounts over a long period of time, there is a chance that there may be an effect, like cancer. Now, let's look at deterministic. Deterministic is short-term effects. You receive a large dose of radiation over a short period of time, and the result is determined. It has been determined that over this period of time, given this particular dose, that you will be experiencing some effect. And this could be early hair loss, or it could be a late deterministic effect, which is fertility, or it could be a late deterministic effect related to cataracts. Either way, it's something that is visible within a shorter period of time, more like an acute effect. So here's a reference slide from the International Atomic Energy Agency website, and it shows you the stages that the cell can go through when it is affected by radiation. So it can undergo cell death, which is an acute effect like I was just mentioning, and that could be cell death. And this is attributed to the exposed individual and the amount of radiation and the linear energy transfer of that radiation. And then there are the stochastic long-term effects, and they can cause the cell to transform over time. That cell could mutate and turn into something it was not originally. Over time, it can lead to cancer, and it's attributable to hereditary effects as well, because it can, like I mentioned, Chernobyl, it can transfer from one individual to the other over time. And then they refer to somatic ovea antenatal, which is both a representation of some cells dying and some cells transforming or mutating or changing its form and the way it responds. And these effects, antenatal, could be somatic, so which means it occurs to the entire body, or it could be transferred from one individual to the other over time. It could be expressed in the fetus or in the live born or descendants of that individual that's exposed. So now we're going to look more closely at how the cell is damaged, or radiation damage occurs on a cellular level. So when ionizing radiation interacts with a cell, ionizations and excitations are produced, and this in turn can cause biological damage. That biological damage can occur as a result of interaction with the water inside the molecule, or it could result because of radiation interactions occurring directly with the DNA or the cell nucleus. Based on where these interactions occur, it is classified as either direct effects or indirect effects of ionizing radiation. So a direct action is usually considered critical because it does damage the cell's DNA, and this can lead to cell death, cancer, and genetic effects. Here lies a Chernobyl victim who received a radiation dose to his entire body, so that would refer to somatic effects of radiation. And this patient received a concentrated or large dose of radiation to a small area during a long fluoroscopic procedure, so this was a deterministic effect. So the extent of the damage and the cell's ability to repair itself will depend on the Q factor of the radiation and where the radiation is deposited or absorbed in the cell. So higher linear energy transfer deposits large amounts of radiation, such as alpha and beta, and low linear energy transfer, which is more penetrating, has less energy deposited in the cells and transfers this energy through the cell more quickly. The biological effects therefore vary depending on the type and the strength of the ionizing radiation. So when radiation interacts directly with the nucleus and the nucleus is damaged, we mentioned this before, this is the direct effect, and the effects on the DNA affects key molecules that is found in the nucleus. Here's an example of what this could look like. Here you can see the rays coming straight through, either interacting with the cytoplasm or the water in the cell, or it interacts directly with the cell nucleus. So during these interactions, one of the base pairs can be deleted or changed or altered. This will alter the genetic code of the cell, and the structure of the DNA can also be affected by breaking the molecular bonds, because this makes it more vulnerable to additional damage. A high linear energy transfer radiation, meaning that it deposits large amounts of energy in a small area, can completely break apart the molecule and lead to cell death. So next up, we're going to be discussing indirect interaction of radiation with the body. Before we get there, I want you to take a quick break, and I'll meet you back here in 10 minutes.